Welcome back. Today we'll continue with this spin system nomenclature and analysis of weak and strongly coupled spin system. Again, this is again a huge topic, but I'll give one or two simple example of three spins and stop for the day. Okay, we will see this. Already we saw AMX three weakly coupled spin systems. I showed you we got 12 lines and we have three combination transitions which do not coupling J information, but combination of all of them together gives you chemical shift information. Now I come across a situation after the AMX, let us say two of them are strongly coupled and both of them together weakly coupled to X. This is called ABX spin system. Remember, A and B are strongly coupled. We already know how to analyze AB. Two strongly coupled spin system. We got four lines, two central lines of higher intensity and outer lines of weaker intensity. We have already analyzed how to get J coupling, chemical shift difference, everything. Now, exactly similar situation will come for AB here. But together individually, both of them are coupled to X. There's a JAB coupling here, JAS coupling and JBX coupling all are present. Now this is a situation, AB part is strongly coupled, where chemical shift A and B are not equal, but delta AB is almost close to JAB. Of course, this is the condition for AB, I told you. And JAB is non-zero. It is visible in the spectrum. Okay. So JAB is non-zero. It has some value. But chemical shift separation is comparable to JAB and chemical shifts A and B are not identical. They are non-equivalent spins. Now AB is coupled to another third spin called X. Now JAX is non-zero. Similarly, JBX is non-zero. They are weakly coupled. Interesting part is, if you see chemical shift of A to X, delta AX is larger than JAX. Similarly, chemical shift of BX, if you consider, delta BX is larger than JBX. So together, AB becomes strongly coupled, and with this, when it coupled to third spin with this condition, it is a weakly coupled spin system. So there is a combination of two strongly coupled and two of them weakly coupled to the third spin together. This is the three spin case ABX, and it is very easy to analyze. AB part we know how to analyze. This is an AB part. Remember, ABX case, AB part contains two AB subspectra and an X part. X part in principle should have 6 lines, but you are getting only, most of the time, you get only 4 lines. It is symmetric with respect to other center. If you carefully see, you can see a peak here, minute intensity. Can you see it? You can still see 6 peaks, but these two generally most of the time, the 2 lines of weak intensity is not seen, only 4 peaks are seen. That's fine. But the AB part is something, we get 2 AB subspectra. Here, can we identify 2 AB? Of course, I colored it. This is one AB part, this is another AB part. So now how to analyze AB part is easy. We know that this is called subspectral analysis. You can do that and get the information. Of course, something more is there. AB spin system gives conjugated solutions. You cannot just like that analyze without taking it according to the intensity pattern. Will not go more into the details. I'm just giving you the information. In the ABX case, you get an AB part and an X part. The X part has 6 lines, symmetrical with respect to the center, and 2 weak transitions are generally not seen. So you get only 4 peaks for the X part. On the other hand, AB part contains 2 AB subspectra, which can be analyzed. And this, if you expand that, AB part can be divided into AB like this and this. And this is a classic example of an ABX. It is 500 MHz proton spectrum of sulfonoxyxenic acid. These 2 protons are chemically non-equivalent, form an AB spin system. They are strongly coupled. But together with this proton, they are weakly coupled. These 2 are strongly coupled. Each of them with this is weakly coupled. So it is a classic example of ABX spin system. As I told you, AB part has 2 AB subspectra and X part has 6 lines, 2 are not visible, so you get 4 lines. This is the example of an ABX. How do we analyze? We can see that. Of course, you can call it ABX or AXY also. Some people call it AXY, doesn't matter. This is strongly coupled and this is weakly coupled. It is analogous to ABX, depending upon how you look at it. You look at this one, this is the AB part or XY part, this is strongly coupled X part. Okay. This is spectrum of malic acid in D2O AXY type. This is spectrum of malic acid again in 200 megahertz. You see the change in this AB pattern. AB pattern gets crowded here, but we can use some tricks in NMR spectrum to see that chemical shoot dispersion becomes better, and that is what is done here by adding a small little bit of excess of this thing NaOD in D2O. You will get better resolution here. So what is this? Very easily you can identify which are the two AB part, which is the two AB spectra. You can identify which are the two AB subspectra, and then analyze this to get coupling information. I don't want to go into the details of analysis. I just wanted to show you the spectrum. When you get such type of spectrum analysis, you have to be careful. This is the AA prime X prime system. I'm giving you a deliberate example of this because it is very useful for you. It is a classic example where AA prime is a situation A and A prime are chemically equivalent. The chemical shifts are same, and there exists a coupling between them which is visible in the spectrum. You got the point? If the chemical shifts are same and couplings are not visible in the spectrum, it is strongly coupled A2. But this is the case, chemical shifts are equivalent but couplings are visible. This is what I said, prime notation for while using Popper notation. This is a AA prime spin system. Similarly, this is A prime X and JAX, this one. So AA prime are strongly coupled. Together, they are weakly coupled with X spin. And such spectra are very easy to analyze. It is an AA prime part. Delta A is equal to A prime. Delta AA prime, the difference delta AA prime is close to JAA prime. As a consequence, they are strongly coupled, and it is non-zero. Of course, coupling must be non-zero. If the coupling is zero, it will become A2. Now, between AA prime and X is A. JAX is non-zero. A prime is X is also non-zero. And this condition validates chemical shell separation should be larger between AA prime and X, so that AA prime weakly couples to X proton. These are the conditions for AA prime X. I hope you are all with me. I am repeating again, the AA prime case, chemical shifts are same and coupling constants is comparable to difference in chemical shifts, and coupling constant is non-zero because it is visible in the spectrum. But together these two is coupled to a third proton, and that coupling, A coupling to X, A prime coupling to X is non-zero, and also the chemical shift separation between AA prime and X is larger than this coupling. So it is a classic example of AA prime X spin system. We can see this in such type of molecules. It is a 1,2-dichloroethylene. We have a cis configuration and also trans configuration. But look at it, we have carbon 13 also present in the natural abundance here. Why I took this example? Because you can use it in your analysis later. Now I'll ask you a question. Look at this molecule. There is a symmetry. These two protons are equivalent. Similarly, if you go along this axis, symmetry axis, these two protons are equivalent, chemically equivalent. But you will not see the coupling. There exists a coupling, but you will not see the coupling. You understand? This is analogous to A2 spin system. Here also coupling is there. Okay, but you will not be able to see this in the proton spectrum, but you can get it in a different way. So in this case, this is cis and this is trans configuration, 1,2-dichloroethylene. If I look at the spectrum of proton, see, this is proton part is AA prime part. See, this is the proton part. What is the type of spectrum you are going to get here? Only one line. Here we get one line because of symmetry. Can I break the symmetry of this molecule? Of course I can break the symmetry of molecule without doing anything. What I will do is, now I will consider carbon 13 also, which is present in natural abundance. If I take this carbon 13, let us say, at any given instant of time, we'll see one carbon, not both are not possible to consider. I will explain to you when I come to carbon 13 NMR. See, I consider this carbon 13 in natural abundance. Now, equivalence is broken. It is not A prime. And this is also because of coupling for this and these are different. So what is going to happen? You are bringing in X coupling, X also, AA prime X spin system. Now the coupling of between AA prime can be seen in the X part also. AA prime X, you can see the coupling in the X part easily. Now look at this one. This is the proton spectrum of cis-dichloroethylene. Single peak is there, which is enhanced in intensity quite a bit. Drastic enhancement in the intensity is there. But if you carefully see this thing, there are two doublets here and two doublets here. What are these doublets? I have not explained to you so far. These are called satellites in NMR. Okay, I wanted to explain to you later, but I just took the example, so I had to explain now. These are called satellites in NMR. Means, take an example of CHCl3. Single proton, you shall get one peak. 99% is carbon to attached, so there is no other coupling, you get a single peak. But there is 1% of the molecule attached to carbon 30. That will couple to proton. So in this proton spectrum, I must see the coupling of proton with carbon. Where do these lines will come? You can split proton into a doublet of very small intensity, 1% intensity compared to main peak. On either side, you will see that. Because it is very small intensity, nearly 1% of the main peak, they are called satellites. Satellites are coming because of the very low natural abundance of the coupled spin. Okay, you can extract coupling information from that also. So we'll go more into the satellite analysis when we come to different type of spectra. But here I just wanted to tell you, these two are called satellites because of coupling with carbon. This proton now, I am taking the natural abundance here. This can couple to this proton. This can couple to this proton also. So I can get all the three coupling. JAA prime I can get. JAX I can get. JAX prime also I can get. Very easily I can measure it. How? Look at this one. This is coupling between carbon and proton. Understand? What is this coupling? AX coupling. And A prime coupling, both are same. Okay. This is AX coupling. It is 198 hertz, about 200 hertz. This is the coupling with carbon 13. You understand the point? This is coupling with carbon 13. I can take this as A prime X or AX, doesn't matter. One of the protons I'll consider. So this, if I measure center of this to center of this, I'll get carbon proton coupling. Which carbon, which proton? This carbon and this proton coupling I am getting. But what about this carbon, this proton coupling? Are they same? No. This is one bond coupling. This is two bond coupling. So A to X coupling is measured here. And remember, you see two more peaks here. What are that? That is coupling of this carbon 13 to this proton, A prime to X. Okay. If this is the larger coupling is AX, this is AX prime. You understand? So this coupling will give me coupling of this carbon to this proton. Now when the symmetry is broken, what about proton-proton coupling, AA coupling? That is also visible. This separation tells me what is AA coupling. Please understand. Now the analysis of this you have to understand slightly in a different way. First, separation from this to this center to this center gives you carbon-proton coupling. Carbon which is directly bonded to proton, you'll get CH coupling. Center of this to center of this gives you two bond carbon-proton coupling. This one. That is on either side you see. But each of the satellite peaks are split into doublets. Why is it so? That is because there is a proton-proton coupling also which is reflected. This separation gives me proton-proton coupling, AA prime coupling, which was invisible in the proton spectrum. Moment you break the symmetry by taking carbon-13 into account, now you are seeing HH coupling. This is the classic example I wanted to tell you. When you have an equivalent spin system, how do you measure the coupling? This was the question I asked you some time back. For example, I took ethylene. I said all the 4 protons are identical. You get a single peak. But still, we know there are 3 different couplings in ethylene molecule. One proton coupled to 3 different protons in 3 different coupling strengths. Then how did we measure that? This is an example. One of the ways is break the symmetry by taking natural abundance carbon-13, or if possible label one of the carbon, then you have broken the symmetry. Then you are going to get all the couplings by analysis of the proton spectrum with carbon couplings will come. That is one way. Okay, very easily. Or go to the carbon-13 spectrum where all these coupling, because your symmetry is broken, can be measured. You understand? So in this case, for example, I go to carbon-13 spectrum here. Then I get a large doublet because of this. And each of this doublet will be split into another doublet because of this. It's a very simple weakly coupled. Okay. So carbon-13 will give 4 lines. So you can measure the separate couplings from carbon-13, or if you measure from the proton, you get this coupling also. Very easily you can measure all these couplings. Okay. Of course, in the carbon-13 you also get, you will not get AA prime coupling. You know why? When I am observing this is an active spin, these two are passive spins. You always get coupling between active and passive spins, but between passive spins you not see. So in the carbon-13 spectrum, you don't get proton-proton coupling. Important point you remember. Okay. So you can now in the proton spectrum, you get CH coupling and proton-proton coupling. Everything is observed here. This is an example for cis dichloroethylene. What happens if I go to trans dichloroethylene? Remember, cis and trans, if I take configuration, this trans coupling is always larger than cis coupling. Very clearly obvious here. See this separation, this J coupling is 5.5 Hertz. Look at this separation. If you measure AA prime coupling, it is 12.2 Hertz. This clearly tells me, if you give me cis dichloroethylene, trans dichloroethylene, I take a proton spectrum, I'll get a single peak. And if you still ask me, how do you identify which is which? I will do a simple analysis of carbon-13 satellites, looking at the proton-proton coupling which is reflected in the satellite spectrum. I know which is trans and which is cis. You got the point now? How to identify cis-trans isomerism by looking into carbon-13 satellites. This is where spin system analysis comes into the picture. So now it is a AA prime X spin system. If you know how to analyze that, you can get all the coupling, 3 couplings which are expected, which you don't see in the proton spectrum. Now in the satellite you see. All you have to do, but you don't do anything. Simply in the normal case we don't see satellites. In other case, simply enhance the signal intensity, see the satellite, analyze this thing, you will get everything. Remember, spectrum of carbon-12 attached and carbon-13 attached, all are overlapped. But only thing is in normal course you don't see it. But if you want to analyze, enhance the intensity. That's why this peak is cut. You have enhance the vertical intensity so that these chota peaks are seen, small peaks. Now you analyze the satellite, you get all the information. This is one example. There are a number of such examples you can see. This can be AA prime X. If I take this molecule, R1 is equal to R2 in this molecule. In this molecule, let us say R1 is equal to R2 again. If I take this carbon-13 instead of this, again AA prime X. Consider this molecule R1 is equal to R2. Consider this carbon. It can so happen. I can make it, if I'm sorry, R1 not equal to R2 here. Symmetry is already broken. Then it is not AA prime X, it is APX. If I consider R1, R2 not equal in this case, and I take this carbon also into account, it's an ABX. See, the substituted ethylenes, cis and trans, depending upon whether the substituents are same, R1 equal to R2, or R1 not equal to R2, Depending upon which carbon you are taking into account, you can identify the spin system as AA prime X or ABX. So this is a tetrachloride benzene. If you take it, you are going to see carbon 13 satellites analysis. You get the coupling between these two. Take a look at this one. If I have this is an A2X, or in this case, okay, in this case AA prime, in this case again A2. So coupling is there, which is not seen here. In this case also, ortho coupling is there, which is not seen. They are chemically equivalent. So if you analyze the 13 satellites of all these molecules, you will get proton-proton coupling and proton-carbon couplings. Everything you are going to see. Now I will give another simple example for AX2 spin system. It's a very easy analysis. AX2 is that proton A is there and X2 is there. Okay. The X2 is chemically equivalent because their chemical shifts are same and couplings are not visible in the spectrum. Whereas A and A is coupled to X or another X equally. That is the AX spin system, AX2 spin system. Delta X equal to delta X, and which is far away from delta A, and JAX is not equal to 0. And this is the condition. Chemical state separation for A and X is sufficiently large compared to JAX. This is called JX2 spin system. AX spin system, this is X2. And in this case, excess coupling is not seen in the spectrum. Please remember. This is a classic example of an AX2 spin spectrum. AX2, X2 part and A part. What is A part? A part is one proton, single proton. Okay. A part is a single proton. But this is coupled to two equivalent protons. Apply your 2ni plus 1 rule. It has to be a triplet. Exactly, it's a triplet. What about the A part? I'm sorry, what about the X part? The X part is coupled to only single proton. It has to be a doublet. So when you get a spectrum like this is a part split into a triplet because of X2, and this is X2 part split into a doublet because of A. AX2 spin system is very easy to analyze. This gives you chemical sheet of X. Center of this gives you chemical sheet of A. This separation gives you AX coupling. There is only one coupling visible. Coupling between X2 is not visible, so you will get only one coupling from the spectrum. Very easy. So these are examples for AX2 spin system. If you look at this, it can be heteronuclear AX2 or homonuclear AX2. In this molecule, if you consider this is this is AX2. This is equivalent spin. This is A. This is X2. This is a heteronuclear AX2. Here again, this is fluorine. This is X2. This is also heteronuclear AX2. Here, fluorine is in the ortho position to both the protons. It is in para position. They are different molecules, but the spin system is same. You call it AX or ATX, doesn't matter. Depends upon how you look at it. Okay. And this is the 19F spectrum of this molecule. Look, in the fluorine case, this is a part, this is X2 part. They are equivalent here. They have perfect symmetry axis here. Look at it. As a consequence, these two are equivalent. This is X2 part. And look at this X2 part. You are going to see 4 lines, and A2 part, you get 2 lines. But if you carefully observe, it is not just A2. See, this central line is split into small doublets. It is not exactly overlapping. In principle, when A2 are perfectly equal, this should be a triplet. See that, it is not triplet. There are 2 doublets. The central peak is not overlap. That means the couplings are not exactly equal. So there is a minute A to B character is also seen here, not APX. Nevertheless, first order analysis is really still feasible here. And this is the A2 part and X2 part. Very clearly see, if you go to higher frequency, this is at 56.4 megahertz. That is about 80 megahertz or so. Now go to 500 megahertz. 500 megahertz fluorine comes at 470. See, now it's a beautiful X part and beautiful A2 part. Everything is clearly seen. Now heteronuclear spin systems, if you consider a molecule like the CH2ClF, now this can be considered as A2 X spin system. In this simple example, there is no fluorine. It is A2 spin system. This is CH2CF2. It is A2 X2 spin system because these are equivalent. These are equivalent. This is A2 part. This is X2 part. Here only protons are there, coupling with chlorine and carbon are not there, so it is a A2 spin system. In this case, this is a A2 part, fluorine is far away, it is a heteronuclear, it is A2X spin system. So this is the way you have to identify the spin systems. And in some example, when the couplings are very, very small and compared to chemical shift separation, these are called ABC, not AMX. All are strongly coupled, but all chemical shifts cannot be individually determined, but all couplings are present in this spectrum. This is a very strongly coupled case where you get 15 lines rather. This is an example of ABC. In this case, in this molecule, these three protons are strongly coupled, and this is the type of spectrum we get at 100 megahertz. The same thing you record at 600 megahertz, look, it becomes AMX. This is the advantage. So strongly coupled will become weakly coupled at 600 megahertz. Even in 600 megahertz, if you carefully see, it is not perfectly weakly coupled. You see, intensities are not equal. Still there is some anomaly. It is minute ABC character is there, but by and large for first order analysis, measuring coupling and other things is okay. Not intensity is different, but coupling constants can more or less get precise. We can get precise. So similarly, you can get AA prime, A triple prime case, where all the three are there in 135 trichlorobenzene. This proton, this this proton have same chemical sheet, but we have couplings present in that. So it is a classic example of A prime, A double prime. This is a A3 spin system. And in the 4 couple K spin system, you look at 1, 2, 3, and 4. All the 4 protons are present. You can think of varieties of possible combinations. And in the one of them is weakly coupled case. All the 4 can be weakly coupled. This we call it as AMPX spin system. Look at this one. We can think of 33 possible combinations here. All four coupled protons. It could be A4, AB3, AX3, any varieties of combination you can think of. And you will get simple case. Simple first order analysis of 4 spin is possible in some cases. A4, first order analysis simple. Only chemical shift, no coupling. A3X, still possible. This will be a quartet, this will be a doublet. Similarly, AX3 is fine. A2X2, this will be a triplet and this will be a triplet. Easily analyzable. AMX2 also. So all these are weakly coupled spin system. They are analyzable in a first order manner. First order analysis is feasible. But the same thing, when you slightly reduce this magnetic field or go to lower frequency, they will become A2BX, ABX2, ABX like this. These are not analyzable in the first order way. So I'll take simple example of AMPX before stopping. If all are weakly coupled spin system, chemical shift of none of them are equal, they are all different. There are 6 couplings present, all are different. First order analysis you can do. Take simple example of furan aldehyde, this molecule. I call it AM and PX. You see the chemical shift 9.6 ppm, 7.7, 6.7, all are well separated. Compared to J coupling, see J coupling maximum you get is 3.7 hertz. Look at the chemical shift separation here. So let us say 7.8 and 9.7, close to 2 ppm. 2 ppm if you take 500 megahertz is 1000 hertz, whereas AM coupling is 0.8 hertz. See, these are perfectly weakly coupled spin system. Similarly, if you look at AP, chemical shift separation is 2.3 ppm. What is AP coupling? Almost, it is 0. It is a fantastic particular case, not 0, means they are unable to measure it because of the line width. So this is the case. In this case, take this molecule, this is A part, this is M part, a P part and X part. Very easily, you can analyze these things. And this is the example of this N-methyl 2-pyridone in acetone disease. See, this is A part, M part, P part, X part is very clearly separated. Intensity anomalies might slightly is there, but easily first order analysis is possible. This is AMPX case. You see more or less equal intensities here, all of them. And I know the chemical sheets of all of them. I can easily measure the coupling constants. So this is an example of a F case where all the three protons are present, all the fluorines are present, and phosphorus is also there. This is heteronuclear AMPS. Phosphorus coupled to three fluorines, all of them are not equivalent. Now this is the F3 part of the spectrum, or fluorine 3, fluorine 1, fluorine 2. So phosphorus I have to record in phosphorus, I have not got the spectrum. But essentially what it tells you is all this thing, heteronuclear spin system forms a perfectly weakly coupled AMX spin system. Very easily you can analyze, take the center of this, you get chemical sheet of this fluorine, and by separation you can get coupling of this fluorine to these and three. Three couplings you can extract easily, taking this also into account. So like this, number of examples that can be given. I don't want to drag further. In last one or two classes, I was explaining about spin system nomenclature and analysis of the proton spectrum. Please remember, these are all very important, especially when you want to analyze small molecules. If you want to get precise coupling information, precise chemical shift information, you should have the knowledge of analysis of the spin systems like this. So with this, I will stop today. And what we am going to do is, I will continue further from tomorrow onwards. Please come prepared with analysis of proton spectra of different spin systems, not like this. Real spectrum recorded I take, and we'll interact together and try to analyze.